Fingham with his Lab 1 report on constant velocity motion. In this video, I will create an experiment to test and record a constant velocity motion. I will use Tracker to observe the data. I will use Visual Python to create computational models to predict motion. Using Newton's second law and the momentum principle, we can predict the future position of a ball if we know the initial position and the changes in time. I will compare and analyze the data from the different results we get from our experiments. Right, so we're inside of Tracker. We tracked it, and here's what we came up with. So we tracked our ball. We made some choices to, we calibrated our calibration stick to a distance of 1 for 1 meter. And we tracked using the center mass of our ball along the this y-axis. When we were done, we found out that it took us 1.3 seconds to travel 1 meter. We made a choice to make sure that our experiment and that our ball was rolling to the right. And at first, when we set our origin, our point of origin, we had some very small numbers in here. So we made sure to calibrate our origin at 0 to make sure that that our origin was at 0 and that we were calculating a positive value to the right. We also measured the ball for a diameter of 57 centimeters or 0.57 meters. We found the mass to be 285 grams or 0.285 kilograms. Taking the measurements from Tracker, we were able to figure out the ball's initial velocity of 0.72 meters per second. The last 2 frames, the terminal velocity was 0.69 meters per second. The average velocity was 0.77 meters per second. And we use Visual Python to create a model that would predict the motion of an object. And we also set our ball's velocity at 0.72 meters per second, which was our ball's initial velocity. We set delta t to be 0.01. The time, we changed that to a value of, we put the average velocity, 0.77 meters per second. And for the net force, we are assuming there's no net force, so we're setting that to 0. And as you can see right here, we're going to use Newton's second law to predict a future position. We're using a delta t of 1/100th of a second, which is a very short time, which will give us a much more accurate calculation as we predict the ball's future position. So we can use this. We can use Python to do the calculations for us. So by using the momentum principle, Newton's second law, we can rearrange this equation to predict the new ball's position. So the new ball's position is the ball's position plus the ball's velocity times the change in time. We ran the experiment, and that's what we got. Okay, so we did several different models in VPython and made several changes to the code. On our first model, we had t at 0.7 of a meter per second, and it ran our model. It predicted the motion to half a meter, which was 0.7 of a second, with delta t at 1/100th of a second. So our original experiment was for 1 meter. So we went back and we changed the t in the Python code to be 1.3, which was the total time difference. And so we ran that model, and that gave us about 130 or 140 calculations for a distance of 1 meter, it took 1.3 seconds. And we did another model. We set t at 3/100ths of a second, or 1/30th of a second, which was the video frame rate. And when we ran the third model, it actually took 1.4 seconds. So the calculation was 1/10 of a hundredth off. So you can see there's a little more error with delta t at 3. And you can see here in the predicted model, there's many more computations and a much level slope. You can see in the observed tracker, there's less computations, or there's less measurements. But again, we see here about the distance of 1 meter, and it took us 1.3 seconds for the observed model, and it took us 1.4 seconds in the predicted model to travel a distance of 1 meter. So that